So our first section we're going to take a look at is 1.1, and it goes over functions and graphs and a little bit on the graphing calculator. So one of the things I'm going to show you in a little bit is how to zoom in and out, which is an important skill we're going to be using all year with the calculator. So this diagram basically goes over all the different kinds of numbers that you would learn in Algebra 1 and where they fit into the big picture. The simplest kind of numbers starting on the inside with the counting numbers and working our way out, we get into more and more complicated numbers. So starting with counting numbers, those are numbers that don't include any fractions or decimals, and they don't include 0. Okay, so they include numbers like 1, 2, 3, 4, 5, just like if you were counting things. The problem with different sets of numbers is that when we start to do arithmetic, we can run into problems. How about John? Can you give me a counting number? 2. 2, sure. And Caleb, can you give me another counting number? 4. 4. Okay, I'm going to do addition. That's the operation I'm going to do here. If I add 2 plus 4, I get 6. Madison, is 6 a counting number? Yeah, that's fine. So that works fine. In fact, addition would always work fine. It wouldn't have mattered what 2 counting numbers any of you told me. If I added them together, I would have gotten another counting. But we could run into a problem with subtraction. Right? Even if we don't do something that complicated, even if we just take the same counting number and subtract it from itself, the answer here is not a counting number. So if all you believed in, if all you understood was counting numbers, something like 3 minus 3 is impossible. Can't do it. So that's where we have to invent something to represent the answer to this kind of problem. And that's the next kind of number set. Those are whole numbers. The only difference between whole numbers and counting numbers is whole numbers include 0. So now you have a symbol that represents the idea of nothing. When you're counting, you don't need the idea of nothing. It doesn't make sense. Right? You wouldn't be counting if there was nothing to count anyway. But if you're counting, the smallest thing you could ever have is 1. You'd never have 0. So whole numbers allow you to do a little bit more things than just count. Right? We can start to get into subtraction. Counting is more like addition. You're adding 1 each time. Subtraction, we're taking away, and we can run into the problem where we get 0, or we can even run into this problem, 2 minus 4. Even with whole numbers, you can't answer the question 2 minus 4. Right? And if I gave that as a problem to someone in like 1st or 2nd grade, they may look at it and be like, I've never seen it where the bigger number comes after the minus sign. Usually the bigger number is always before. So they'd say, I don't know how to do that. You're taking away more than you have. So that's where we invent our next set of numbers, and those are called integers. So integers now include negative numbers. Right, so now you could give me any integer, any other integer, and I can add and subtract them all day long. I've never run into a problem. No problems at all with adding and subtracting if we only stick to integers. But then when we start to get into division, something else can happen. Yeah.
Oh, so would some of them be in the same category sometimes?
So it's kind of like if you think about you're in a specific state. You're in Massachusetts. Well, you're also in the United States. You're also in North America. You're also on Earth. So it's the same thing here. Counting numbers are also whole numbers. Whole numbers are also integers. Integers are also rational numbers. Anything that's on the inside automatically has all the classifications of everything on the outside. Just like you're in Massachusetts automatically means North America, Earth, Milky Way. It doesn't work the other way though. Just because you're in North America, it doesn't automatically mean you're in Massachusetts. Right? Just because you're a rational number does not mean you're a counting number. But if you're a counting number, you are a rational. Any question on that? Okay. So integers allow us to do or represent the idea of less than nothing, right? So starting to get a little bit more theoretical now. Maybe negative numbers aren't something people use in everyday life. Might use them if you owe someone money, like a debt. You think of that as not only do I have $0, I have even less than 0 because I owe somebody money. So it's a negative. But let's just take these two integers right here. And instead of doing addition or subtraction, let's do division. If you take 2 and divide by 4, that's a problem, integers. You can't do it. Because integers don't have decimals or fractions. So that's our next set of numbers. Rationals give us the ability to have parts of a number, or fractions. And for most people in everyday life, rational numbers are about as complicated as you get. When you buy something at a store, it might not be $12, it might not be $13. It might be $12.50. $12 and then a fraction of the next. When you're cooking, you might not need 2 cups of flour, you might not need 3 cups, you might need 2 1/3. Something in the middle. So now we can pretty much do addition, subtraction, multiplication, and division. If you give me any rational number, 2/3, and another rational number, 5. 5 is rational because you could make it a fraction, like that. You could put a plus, a minus, a divide, or a multiply sign, and you'd get an answer that would be rational. You wouldn't get anything outside that box. So the problem comes in when we start to do things like this. That's another math operation. It's a math operation that only takes one number. Addition, subtraction, multiplication. Those all take 2. It only takes 1. And that's a square root. If you try to do something like that, and all that you understand is numbers that can be written as fractions, decimals, positives, and negatives, rationals, you can't do that. You could do this, that's fine. You could do square root of 9, you could do square root of 16, you could do any of the perfect squares, but you couldn't take the square root of numbers in between the perfect squares. So what we have is another type of number, and it's called irrational. So an irrational number is a number that cannot be written as a fraction. And when I say it can't, I mean it never will be able to. It's impossible. So if you think, well, maybe someday we'll figure out how to write the square root of 3 as a fraction, no, we won't. You can prove that it will never be able to be done. So there's no way to ever write that number as a fraction. And not a lot of people use those kinds of numbers in everyday life. Numbers that can't be written as fractions. There might be a couple exceptions, but even if you can't write a number as a fraction, like say you're using like a CNC machine to make a part, you got to round it off somewhere. I mean, you can't have 600 decimal places and plug that into the machine. I mean, the machine probably can't even be that accurate. Maybe a machine can be accurate to the 10,000ths, the 100,000ths, maybe a millionth. I don't know. But you can't be accurate. You just don't have that kind of precision. So eventually you got to round things off. But there are a couple numbers that are irrational that are kind of well known. Any of the square roots that are not perfect squares. And there's one other number that's used a lot that's irrational. Anybody know that number? John? Yeah? Pi. Yeah, pi is a number that is irrational. And anytime you're doing stuff that could be circular or spherical, the number 3.14 is going to come up a lot. But for most purposes, if you round that to maybe 7 or 8 decimal places, that's going to be more than enough accuracy that you need to like machine a part or something like that. Right? And now, if you take all the numbers that can be written as fractions and all the numbers that cannot be written as fractions, positives, negatives, all of them, though it's called the real number system. Right? And those are the kind of numbers that we're going to be sticking with through the first chapter. Real numbers. There are other kinds of numbers beyond real numbers. That's when you get to algebra 2, but we'll talk about those later on. So I just made a few notes about some of the number systems. So again, a rational number is a number that's a fraction, where the top and the bottom can be represented as integers. So technically, you would not write a rational number like this. Kind of weird to write something like that. If you're going to do that, you'd probably do that instead. And then if you could reduce it, you can. But this is like a fraction that was reduced too far. You got decimals. So generally, when we have a fraction, we leave the top and the bottom number as integers. And of course, the bottom number can't be 0 because we're never allowed to divide by 0. And symbol, I think I do that on the next page. Yeah. Different number sets have symbols: the rationals, the integers, and the reals. Those are 3 number sets that have special symbols we can use. So integers kind of looks like a capital Z with an extra line in it. That's the symbol for integers. Rational numbers, Q, kind of that vertical line in it, and real numbers, capital R with that extra line on the left-hand side. So if I wrote something like this, what do you think that symbol would mean? It means positive integers, right? I'm looking for something that's a positive integer. I could put a minus sign there and have it be a negative integer. So you may see that when you're answering a question, it may say something like, only list these answers. Well, that means they only want positive integer answers in your problem. The other number systems, like number categories, irrational, counting numbers, I don't know of any symbol for those. These are the 3 that we use a lot. So I kind of touched on this earlier when I talked about operations, and I brought up square root. I said square root is an operation in math that only takes 1 number. Okay. Well, the other operations, addition, subtraction, multiplication, division, they each take 2 numbers. You can't do this and tell me the answer. 3 plus what? 3 plus, you need another number to add to it. So those are called binary operations, because they take two numbers as input, and they give you an answer. So we're going to look at a few properties, just kind of naming what they are. And I'm going to give you guys some formulas, and I'm going to use the letters A, B, and C. A, B, and C, and the formulas I'm about to show you, could represent any real numbers. That means they could be positive, they could be negative, fractions, decimals, 0, any real number, square root of 5, anything like that. So let me show you the property on the right and see. The first one's kind of tough. Probably won't know that one. So the first property is closure. So closure means that when you perform an operation on 2 numbers, you get an answer that's within the set of numbers you started with. So in other words, if you add a real number to a real number, you will get a real number. Let me show you an example that closure doesn't work. Subtraction with counting numbers. The subtraction operation with counting numbers doesn't obey that closure property. What that means is you could give me a counting number, you could give me another counting number, and the answer that I get is not a counting number. That's a counting number, that's a counting number, the answer is not. If closure was going to work, that means the number you start with is a counting number, next number is a counting number, and the answer has to be a counting number. The answer has to be in the set of numbers you started. With real numbers, it always is. Add, subtract, multiply, and divide any real numbers you want, and the answer you'll get is a real number. Right? how about that one? A plus B equals B plus A. You're changing the order, you add two things in. Anyone remember what property that is? John?
Commutative property.
Yeah, very good. That's the commutative property. He specifically said of addition because there is one of multiplication. That would be like A times B equals B times A. I think at the bottom of this page I mentioned there are all these properties again for multiplication, but they're in your book on page, and I tell you the page. So I don't write them all down. How about this one? This next property doesn't have to do with order. It's ABC, ABC on both sides. It has to do with grouping. The order, it has to do with what did you do first. And with addition, it doesn't matter what you add first. Anyone remember another property you usually study with commutative? Anyone remember that one? Yeah?
Associative?
Very good. Yeah, Julie, right? Yep. It's associative. So associative, think about the first part of the word, kind of associate. Who you associate with is kind of like saying, who's your group of people that you talk to? Who's your group of people you hang out with? What do you associate with? So associate has to do with grouping things. Parentheses are a grouping symbol. This one, a little bit harder. Let's see if anyone remembers the name of it. It's the idea. It's the operation that you can do to something and it doesn't change it. You get back what you started with. So for addition, it's adding 0. Adding 0 to something does not change its value. Anyone remember the name of that one? That's the identity property. Now for multiplication, you wouldn't use a 0. What number would be involved with the multiplication identity property, Michael?
1.
It'd be 1. X times 1 equals X. That's the identity property for multiplication. So a little bit different, but pretty similar. This one, and again, maybe a hard name to remember, but this is the inverse property. The inverse property for addition says, what can you add to a number to cancel it out, to get 0? And it's basically its opposite. If you add opposites together, you get 0, and that's the inverse property. How about this one, where you have an A on the outside and a B plus C, and then you end up with AB plus AC? Yes, Lindsay?
Distributed?
Yep, that's your distributive property. And then a lot of these properties are also listed again on page 2 for multiplication. There is no such thing as distributive for multiplication. You don't do that. Like if you had this, you definitely don't do 3 times 3 and 3 times 4, no. You just do 3 times 4 is 12, 12 times 3 is 36. That's how you do that. Okay, any questions on those properties? Okay. So, an equation. That's not an equation. What I just wrote there, that's an expression. Specifically, that's an algebraic expression. That's a numeric expression. To make something an equation, you have to have an equality symbol in it, or an equal sign. These are all equations. Each one of those 3. Let's start with the one in the upper right, the 5 equals 2. Any thoughts about that one? 5 equals 2? Yep, Lindsay?
Well, that's not true.
It's not true, that's a contradiction. That's an equation, it's just not true. You might end up with an equation like that if you had something like, if if you go to solve that equation, you're going to end up with 5 equals 2. So that's called a contradiction. And that usually means that it's an equation with no solution. Okay, but this is a contradiction. This one, 3 plus 4 equals 2 plus 5, that turns into 7 equals 7. That's an identity. An identity is an equation that is always true. You can't find a value that would make it false. So this one is an identity. So we got an equation that's always false. We have an equation that's always true. Now, how about 2x equals 12? Is that true or false? Yeah, Madison? It depends on what you pick for x. There's a condition that could make it true. So that's called a conditional equation. If you pick 6, it's true. If you pick anything else besides 6, it's false. But they're all equations. So now we're going to look at some properties that involve equations. Okay, same deal as last time. A, B, and C are going to represent any real numbers. So these properties apply to positives, negatives, fractions, decimals. And these properties you might remember from geometry. You see them in there as well. The first one says that something equals itself. Begins with an R. You want to remember that one, Tim?
Reflexive.
Yep, that's the reflexive property. So what that basically means, if you write x equals 2 or 2 equals, oh, I'm sorry, that's the next one. What that means is that something is always equal to itself. You might use that when you were doing a proof with triangles, and you had a side that was shared between the two. You could say that the side equals itself because it was the same side in both. And that's reflexive. How about the next one? This one is like saying if x equals 2, then 2 equals x. Remember that one, Tim?
Symmetric.
That's the symmetric, yes. So that's another property we can use with equations. And then the last one, it has to do with a chain of things. And sometimes you can have more than, so I only have 3. But it says if A is the same as B, and B is also the same as C, then A and C must be the same. This is like the conclusion that you can infer from the 2 statements. Yeah, Caleb?
Is that the transitive property?
Transitive. Yep. So reflexive, symmetric, and transitive are 3 properties that apply to equations. The properties we went over on the previous page apply to expressions. So, this kind of question I'm about to show you can be one of 2 ways. Basically, I'm going to have you solve that to a point, and I want to know the name of each step. So I can either give you the names of the steps, and you show me the work for that step, or I could give you the work, and you tell me the name of the step. Let's do it. Let's do it where I'll give you the name of the property, and then you tell me how to do that. How about Mabel? Could you tell me if I want to do distributive property, what would be my first step?
Distribute between would be 2x plus 3.
So it would be, and we don't even have to simplify. So just, what would I write down?
2x plus
Plus, and what would you get before you had 6? Like, how did you get 6? 2 times 3. So distributive property is literally just taking the 2 and multiplying it to each thing, not even simplifying it. That's actually going to be my next my next step, which I know we normally do all at once. Now I'll write down what Mabel said. So it would be 2x plus 6. Now, without me showing the last property, does anyone remember the name of what property would allow me to say that those are equal? I mean, they don't look exactly the same. It's 2x plus 6 and 6 plus 2x, but there's a property you can use there, Michael.
Is that the symmetric?
Yep, that would be, well, so symmetric, go back here. So symmetric would allow you to switch what's on each side of the equal sign. So that would allow me to take all of this and put it here, and all of that and put it there. So then on the left, I would have 6 plus 2x, and on the right, I would have 2x plus 6. But it wouldn't actually change the order of the expression on each side. Anyone remember what other property allows us to switch the order two things are added in?
Commutative?
Yep, the commutative. So if we use the commutative property just on that part right here, 6 plus 2x equals 6 plus 2x. So solving a very simple equation, just justifying the reason why you did what you did at each step. Okay. Okay, so coordinate system. So basic one-dimensional, not even two-dimensional coordinate system. Okay, number line. Usually we put 0 right in the middle. Convention is to have positive numbers go right, negative numbers go to the left. When we get into 2D, which we'll do in a second, then we have to add in another axis. This is just a one-dimensional coordinate system. And what a number line allows us to do is basically give order to numbers. We can say this is a bigger number than that, this is a smaller number than that. Without a number line, we can't do that. Does anyone remember the name, the group? There's 4 symbols that we use that describe whether numbers are smaller or larger. But there's a group, there's a name for all 4 of them beginning with an I.
Inequalities?
Inequalities, they're your inequality symbols. And those are the 4 inequality symbols that we use to describe a relationship between 2 numbers when we're comparing them. Greater than, less than, greater than or equal to, less than or equal. All right. Any questions on the name of our 4 inequality symbols? So, when graphing on a number line, there's a couple ways we can do it. Like if you wanted to graph, say, x is greater than 2. One way that I think a lot of people are familiar with is open circle, closed circle. Right? So when you're graphing on a number line, we always use an open circle for a greater than or a less than. We use a closed circle or a filled-in circle for greater than or equal to or less than or equal to. Okay, so what the difference means is when you have a filled-in circle and I say x is greater than or equal to 10, that means I can include 10. So if I said you have to be greater than or equal to 10 years old to go on the ride, that means you could be 10 or older. If I said you had to be greater than 10, we're just talking about integers. Greater than 10 means then you have to be 11 if you were working with it. All right, so let's try an example of graphing. Well, let's start with that. X is greater than or equal to 2. That's the preferred way that we like to write an inequality. This is the same thing. Pointing at the 2, pointing at the 2. Does anybody know why we like to do it the way that's on the left? Has to do with when we graph it, yeah.
It ends up pointing in the direction that the line is going.
Yes, if you put the variable, then the symbol, then the number, the symbol is going to tell you which way to draw your arrow. If you do it the way that's on the right, over here, it's going to tell you the opposite way. So we prefer to put the variable on the left. So if you have a number line that's blank, you have to number it. On Edge Elastic, usually I give you a number line that's already numbered for you. But the first choice you have to make is what kind of circle and where it goes. So, Annalise, what kind of circle would I use here? Open or closed?
Closed.
Closed? And, well, I was going to ask you what number to put it on, but it does go on 2. And Nick, which way do I shade?
Right.
Yeah, that way, if I shade, I mean, which way do I point an arrow? And that represents every number greater than or equal to 2. Let's try one like this. So this is one where if they give it to you like this, I would rewrite it like that. Instead of saying 3 is greater than y, when you rewrite it, you still want it to point at the variable it was pointing at originally. So it's still pointing at the y. And now, as Michael said before, that's going to tell you which way to shade. So Leanne, what kind of circle would I use on 3 this time? Yep, I'm going to do an open circle. I got to put some numbers on here. There's lots of ways you can number your number line. I'm just going to call it like that. If that number was like 30, maybe I would have gone by tens or something like that. Okay, so open circle. And how about, Tim, where's the open circle going to go? What number?
On 3.
On 3. And John, which way is the circle going to, which way is my line going to go?
Right.
Um,
It would be cool. Because the variable always comes first, just in the first.
Correct. So which way?
The left.
To the left, yeah. Y is smaller than 3.
Sorry, I got tripped up because I saw the other one circle.
Yep. So y is smaller than 3 means you can pick any number that is smaller than 3 but not including 3. Okay. Questions on that? Okay. So we're going to do the same 2 problems again. I'm just going to show you a symbol that you're going to see in our book. A symbol that you can use in place of a closed circle is a bracket. So if we were doing this using that symbol, we would use a bracket on the number 2. Now the thing about the bracket is you have to choose which way the bracket faces. The bracket is always going to face in the direction you're going to shade. So from the notation in our book, it would look like that. That's exactly the same as putting a closed circle on 2 and shading right. So brackets can be used in place of a closed circle. Anyone have a guess what might be used in place of the open circle in this style? Yep, Lindsay?
maybe a parenthesis.
Yep, it would be a parenthesis. So, same thing. We could put a parenthesis, but you have to think ahead a little bit. You have to think which way you're going to shade. We already did this. We know we're shading left. Parenthesis on 3. And then shade to the left. Right? Either notation is fine to use. I think Edge Elastic is going to use the open and closed circle. When you're doing homework, you can use either notation. Just to be used to seeing both. All right. Now, a statement like that, if you pronounce it, you use the word and. The way I pronounce it is I usually start in the middle, and then I read it each way. I say x is greater than or equal to 2, and less than or equal to 9. Anyone remember what that's called when you have the word and? If you had the word or, it would be called a disjunction. Like x is less than 0 or bigger than 10. It's called a disjunction. Anyone remember what it's called when you had the word and? Nancy?
Is it a conjunction?
Yep, it's a conjunction. So this is a conjunction. And the thing what you can do with a conjunction is this is kind of the nice short way to write it. If you want to break it apart, you can. And the way you break it apart is that's one part of it, and that is the second part. So if you put what's in the black box, x is greater than or equal to 2. That's what from the black box. And then from the green box, x is less than or equal to 9. Of course, when I wrote the black box down, I put it in the order that we normally like to see it. But you should be comfortable with taking a conjunction and either splitting it apart or taking two and combining them together. So let's graph that one. Now, I said you can use either notation, open circles, closed circles, or the brackets, parentheses, but don't mix them in the same problem. If we're going to do circles, let's stick with circles. Let's go. Right, so Caleb, what kind of symbol could I put on 2?
Favorite circle we said?
You can use either notation.
Closed circle.
All right, so we're going to use the circles. So closed on 2. Madison, what kind of circle on 9?
Closed circle.
Another closed circle. And Sophie, where am I going to shade?
You're gonna shade 1, 2 to the right, 9 to the left.
So
So the in between one.
in between, yeah, this is one that when you shade, it doesn't end up being an arrow pointing in a direction. It ends up being a line segment just connecting 2 dots. So it's a between. It's exactly what a conjunction is. It's a between. Okay, any question on that? So I know lots of different things we're doing right now. But again, this section is really, I don't think you're going to see anything new. So we're just kind of going through some review stuff quick. I'm sure you guys remember it. All right, absolute value. What's the symbol look like for absolute value? What does that look like? Yep, Leanne?
Brackets.
Like this?
Well, like straight line.
Yeah, just straight lines. So just 2 vertical lines, just like that. So if you want to think about it geometrically, it's the distance from 0 on another line. Since I use the word distance there, what kind of number is distance? It's always what? Yep, Julie?
Positive.
It's always positive. Okay, so absolute value is always a positive number. I guess it could be 0 if you want to know the absolute value of 0. We use 0, which technically is positive. But it's never negative. We could say it that way. You never get a negative number. You always get a 0 or higher. So let's think about it. Let's think about it a little differently. If I gave you a positive number to take the absolute value of, what would you do to it? What would you have to do to it? If I gave you a positive number to take the absolute value of, what would you have to do to that number to get the answer?
Nothing.
Nothing. So, if I gave you a positive number to take the absolute value of, the answer would just be the original number I gave you. You wouldn't have to do anything to it. Now, what if I gave you a negative number to take the absolute value of? What would you have to do? Yeah?
Make it positive.
And what would make it positive by you taking the what of the number? Making the number its opposite. Yeah, you make it its opposite. So if you have a number that's less than 0, that's negative, and you want to take the absolute value, then the answer would be the opposite of the number that you started with. So that's a little bit more formal way to think about absolute value. If it's positive, just write down the original number you had. If you started with a negative number, the answer is the opposite of the number you started with. And if so, like let's say you had -2 here. Following this formula, it falls into case 2. You're starting with a number less than 0. So the answer is the opposite of the number you started with. The opposite of the number I started with. And a -2 is +2. All right, a couple quick examples on that. How about absolute value of 6? What would be the answer there? Yep, Maddie? 6. Just 6. And the absolute value of -3 would be, yeah, John?
3.
Just 3. Nice. Simple concept. So where you can use absolute value is if you want to know how far apart two numbers are on a number line, you just subtract them. It doesn't really matter the order you subtract them in. You might say, well, we talked about commutative earlier, and you said the order doesn't matter when you add. Are you saying the order doesn't matter when you subtract here? Yes, I'm saying that here because of these bars. 2 minus 5 and 5 minus 2 are different answers. But not if you take the absolute value. They come out the same. So if you want to know how far apart two numbers are on a number line, you just subtract them and take the absolute value. All right, so let's try that with this. Find the distance between the two numbers -2 and -9. So can anyone set up for me what the formula would look like when I fill in the values that I have an example for? Yeah, Nick?
-2 minus -9, but like the -9 has a parentheses and minus sign.
Yep, so -2 minus -9. Now think of those absolute values as like a grouping symbol. We have to do what's inside there first. What happens when you have minus? Turns into what? Positive. So this is really -2 plus 9. And how about, Maddie, what's -2 plus 9? 7. So I haven't done the absolute value yet. I just did what's inside, but then the absolute value of 7 is 7. So that means the distance on a number line between -2 and -9, it's a difference of 7 units. Any question on that? All right, so two-dimensional coordinate system. A little bit more complicated than one-dimensional. We're going to talk about a Cartesian coordinate system. It's not the only coordinate system, but we're going to talk later on in the year when we get to chapter 9 about what's called a polar coordinate system. That's a little different. But Cartesian has two axes, two number lines intersecting at right angles, called the x and the y axis. Where they intersect, that's called the origin. And for the x-axis, it's just like a number line. Positive direction is right, negative direction is left. For y-axis, positive is up, negative is down. Now I don't have it on the board, but does anyone remember the name of the axes divide the coordinate plane into 4 regions? I've labeled them with Roman numerals. Anyone remember what those 4 are called? Julie? They're quadrants. Just like in 3D, when you have an x, a y, and a z-axis, you have what are called octants, because you have 8 regions. But in 2D, it's a little simpler. You have 4. What I've done in parentheses is I've labeled basically the direction of this is your horizontal. And the second number is your vertical. Does anyone remember what you call this thing? When you put two numbers with a comma and parentheses. There's a couple things. Yeah.
Coordinate pair.
So it's actually kind of combining both names. So it is a coordinate. And if I said specifically what kind of coordinate, it is an ordered pair. Like in 3D, you have ordered triples because you have an x, comma, y, comma, z. But this is the general term is a coordinate. Specifically, it's an ordered pair. Just said that. Coordinate or ordered pair. And up until chapter 9 or so, all the graphing that we're going to do is going to involve this type of coordinate system. So just about. Okay, I'm going to show you guys a little bit about zooming on a graphing calculator. So the reason why we might have to zoom, you don't have to do this part, you can turn your calculator on, but you can just watch this part. The on is in the lower left. If you had stuff on the screen from the previous person that used it, the clear button is in the upper right below the four-way arrow. And press clear. If you're ever on a screen that you're like, wait, how do I get out of this? I'm pressing clear, it's not getting me out of the screen. What do I do? If you press second and the mode button, it says quit. So that will always return you back to the main screen if you have to go back. But let me show you why we have to zoom. And again, you don't have to worry about how is he doing this right now. So I just typed in a graph. And the calculator is drawing it. I can tell it's drawing it because there's a little yellow circle in the upper right and it just disappeared. It's done. Where is it? It's off the screen. So a lot of times, the calculator it doesn't know where you want to look. It'll draw whatever you want it to draw, but you have to look in the right spot to find what it drew. In this case, I graphed x squared plus 10. That's a parabola. So it should be a U shape. But this plus 10 moves it 10 units up. Now, the standard window on the calculator, meaning the standard screen that you always see, is negative 10 to positive 10 on the x-axis and negative 10 to positive 10 on the y-axis. 10 units left, well, I guess 20 units left and right, 20 units up and down. If you don't want that, you need to change the window. So I'm going to show you how to type in a specific window. And what I'll do is I'll have you guys type in the same graph that I did so you can see something on your screen. All right, so what you want to do is from that home screen, press Y. Is everybody at a screen that has all those different colors on it? Anybody not at that screen? Okay, so now we're going to press X. X is right below the mode button. It's go down one row and over to the right one row from the blue button in the upper left. So press X, and now we want to do an exponent of 2. That number is 5 down, 4 down on the left. So x squared. And then I'm going to do plus 10. So plus is over on the right-hand side above enter, and then we just type in 10. We're not going to hit graph it, because we already know it's up the screen. What we're going to do is we're going to change our window. So what button up at the top, those 5 gray buttons at the top, which one do you think you're going to press to change the window? So we're going to press window. And it gives us some different options. The X-min, the X-max, the Y-min, and the Y-max, those are the most important. The X scale and Y scale, that just says how often do you want to see a tick mark on the screen. That's not really important, because we don't actually measure anything with the tick marks on the screen. So you'll probably never see me change that. But what we want to do, when you see something like this, that means the x min. The next number is the x max. So the first set of brackets are always your x-axis numbers, and the second are your y-axis. It's important you put them in the right order. If you try to make the minimum bigger than the max, that won't work. You'll get an error. So we're going to do negative 20, 20. And then we're going to go down to y min and negative 20, 2. Let me do negative 50 just to show you what happens. I tried to make the max smaller than the min. You can't do that. It's going to say window range error. And it basically gives you a hint. It says check to make sure that your maximum isn't less than your minimum. I'm going to go back. I'm going to quit. It says press 1 to quit. I'm going to go back to my window, and I'm going to type in what I should have, which was negative 20. What did I do? Positive 20. Okay. So now I've typed in what they told me to type in for those 4 numbers. Now go ahead and hit graph. And you should see the parabola now. Just like that. Did people get that graph on their screen? Yep.
It's not letting me go down.
It's not letting you go
It's
down?
not.
Let me see. So press 1 because you have to quit the number 1 on that thing. And now you can go back to your window. So it looks like, yep, now just type all those numbers.
It's still not letting me.
It's not letting you? Let's see. Go back to window. So negative 10, positive 10. So this is the down. That's that. Oh, okay. I think go back again. Show me what button you pressed for the negative symbol. Don't press it yet. Just point to which one you pressed. Okay. So there's a difference on the calculator between the minus and the negative. So a good point. That's minus, meaning you want to do subtraction. That's the negative symbol. So when you want to do a negative number, it's the one that's right below the 3 next to the decimal. Did it let you go down now?
Yeah.
Okay. Yep, so there might be little things like that I forget, but I'll remind as we go. So just remember that. So we weren't seeing before because that was the window before. Now we've expanded the window so we can see what was off the screen. Okay, the scale, you don't have to do this part. I just want you to watch. Basically, we'll keep that right there. If I change the scale to 5 on the x-axis and just compare it to what you had before, I didn't wait for it to draw. That's why it didn't. If I had waited, it would have drawn it eventually. All it does is change how often you see a tick mark. 0, 5, 10, 15, 20. I don't really see much of a reason to mess with the scale. We don't really do that much. Okay, question on that? So that's basic zooming. You might think, well, that's pretty easy, but sometimes zooming is hard because you don't know where to look for something. You may have something that happens off the screen at 200 on the x-axis. Well, how do you know to look over at 200? Well, that's where practice and that's where the algebra part comes in. Because a lot of times when we do stuff algebraically, we'll always do a little bit on paper before we graph it. The algebra kind of gives us a hint at where something could happen off the screen. The calculator helps us see what's happening. If the calculator isn't, it's not going to be a substitute for actually knowing how to do the math. You still have to know how to do stuff, or the calculator won't help you. All right, so last thing we're going to look at is what's called the distance formula. Kind of like what we did in a single dimension, but this is 2D, finding the distance between 2 points. All right, so suppose we have 2 points, x1, y1, x2, and y2. And I'm going to make a picture of that on the next page. I'm going to ask a question to see if people can make a connection with something. And I'm going to put that back up. So let's say we have a point here, and it has a coordinate, has an x and a y value, and another point here, called x2 and y2. And I want to figure out how far apart those 2 points are. Exactly how far apart. Now, if it went like this, that'd be easy. All I'd have to do is count 1, 2, 3, because it's straight on the grid lines. But do you have an idea how we could figure out exactly how far apart those 2 points are? Yeah?
Draw like a line from the bottom one, right? Basically make a triangle out of it.
Yeah, make a triangle out of it.
And then you count the straight line and you Pythagorean theorem for the diagonal.
Exactly. We're going to just use the Pythagorean theorem. The bottom side is easy to figure out. It's 1, 2, 3, 4, 5, 6, 7. The height, that's easy. 1, 2, 3. So now all we have to do is use Pythagorean theorem. So this bottom side, this 7, would come from doing x1 minus x2. That's basically what it is. It's x1 minus x2. Or you could do x2 minus x1. That order doesn't matter. But you're finding the difference between this x value and this x value. And the same thing with the y's. You're finding the difference between this y value and this y value. How far up did you go? 1, 2, 3. And that's where the distance formula comes from. Now you might notice I don't have any absolute values. I have the x1 minus x2 gives me the length of the bottom of the triangle. The y1 minus y2 gives me the height. But how come I don't need absolute values? What's in that equation that it makes them unnecessary? Yeah.
The square, which if you multiply something by itself, it's always going to be positive.
Exactly, that's square. Pythagorean theorem, you have to square. You have to square the two lengths, add them together, and then take the square root. Well, anytime you square something, it doesn't matter if it was positive or negative to start, it's positive now. So it would be redundant to do something like this. Not wrong, but redundant. You don't need that. Right? And that's your distance formula. So we were going to find the distance between 2 points. Call this x1, y1, x2, and y2. What I usually do is I just start out and I write the whole formula down so I don't forget anything. And then I fill in. x1 is 1. x2, 5. y1, 4. y2, 6. And I just chose to have the first coordinate be the x1 and y1 and the second one to be the x2 and the y2. It wouldn't matter if you switched that. It would have just made it 5 minus 1 and 6 minus 4. Wouldn't have made any difference. So we end up with square root of 1 minus 5 is negative 4, square root of 16. 4 minus 6 is 2, squared is 4. So we get the square root of 20. And if we simplify that, what is the square root of 20? Not as a decimal, but how does it simplify as an exact answer? Yeah, Lindsay? 2 times the square root of 5. There's different ways you can go about it. You can break 20 up into 4 times 5. You try to break it up into a number that you can take the square root of nicely in your head. And the square root of 4 is 2. So anytime we have a square root, we'll generally want to simplify it like that. That's what they mean when they say simplify. If they want a decimal, they'll say round, whatever, round to 2 decimal places. All right, and the last thing is the midpoint formula. So the distance formula tells you how far apart 2 points are. Midpoint formula tells you where the middle is. Anybody see what am I really doing right there? I'm adding 2 things up and dividing by 2, but what is that? It's the what?
Averaging.
Yeah, it's averaging. That's all that the midpoint formula is. It says basically what's the average of the x's, what's the average of the y's, and that's what's in the middle. All right, so let's finish up with this one. So we're going to find the midpoint between -5, 2 and 3, 7. Again, just think of what's the average of the x's and then the average of the y's. Okay, what's the average of my x values? -5 and 3. What is it? John?
-2.
So -5 plus 3 gives me how much?
Negative.
-2, and then divide by 2.
Would be -1, sorry.
-1. -1. And what about the average of my y values? Yes, Caleb?
4.5.
4.5. You could write it as 9/2. You could write 4.5. In edge elastic, it wouldn't matter as long as you wrote a number that is equivalent to 4.5.
Which do you prefer?
I'm fine with either one. Either one. I don't know if you could do it as a mixed number in edge elastic when we do tests. I mean, most people wouldn't do something like that anyway. I'd have to specifically set the button up to do that. So if you don't see that button for a mixed number, then you're going to have to do either a decimal or an improper fraction or proper fraction. All right, so lots of different stuff there, but hopefully nothing you haven't seen before. Just kind of review. So the homework for tonight is those questions on page 11. Okay, that will be posted on YouTube in about 15 minutes, as long as everything goes to plan. And the last thing I just need to show you with the calculator is how you turn it off. Sometimes if you don't turn it off and you put it back on the charger, it just stays on. So to turn the calculator off, you press the second button in the upper left, and then you press the on button in the lower left. Second, on. We'll shut it off. Okay, and when you're all set with your calculator, you can, let's have the 2 rows closest. You guys can put yours back first. Just make sure you have the screen facing out. And you put it back in the right slot.